All right, open up your book to section 14-4. We're on page 714 in your book. And the title of this section is Probabilities of Various Permutations. Our objective here is given a description of a permutation. Find the probability of getting that permutation if an arrangement is selected at random. All right, so let's start off by talking about what exactly a permutation is. And a permutation is an arrangement in a definite order of some or all of the elements in a set. And that's the key there, is when we talk about a permutation, is that there is a order to this. We'll talk about a combination in the next section. And when we deal with a combination, we'll see that the order does not matter. This is what distinguishes these two topics here. So we're going to deal with permutation first in this section. And with a permutation, the order matters. It's an arrangement in a definite order of some or all the elements in a set. So order matters. All right, so let's take a look at an example here. If you look at example 1 there on page 714. Example 1 says, in how many different ways could you arrange 3 books on a shelf if you have 7 books to choose from? All right. So we're trying to arrange 3 books on a shelf from a total of 7 books to pick from. So let's talk about really the 3 events that we've got going on here. Event A is arranging the first book, or picking the first book that we're going to put on the shelf. That's the first thing we got to do. And then once we have that one put on the shelf, then we can pick the second book. That's the second event. And it says we're going to put 3 books on the shelf here, so that means we have a third event here, which is to pick the third book. Okay, so those are the 3 events that we're talking about that we've got to take care of here. So we're trying to find the number of ways of arranging 3 books. So the number of ways of arranging those 3 books is really the number of ways these 3 events here that we've just written down could occur. It's the number of ways that event A can occur, and event B can occur, and event C can occur. Got 3 events here that we're dealing with. All right. The fact that we're saying that all 3 of these events have to occur, this is using the word and to describe that. It's another hint. We know we're going to be multiplying these together. These are either independent or dependent events. That's what we got to figure out next, but we're going to be multiplying these together. Well, when we go to calculate this, the first book, of course, doesn't matter. You can pick anything that you want. But once I pick the first book, this is like picking cards from a deck and not replacing those cards. There's fewer books out there now to pick from. So these are dependent events. So when I multiply these, I got to multiply by the number of ways of picking the second book, given that I've already picked the first book. And then finally, you have to pick a third book. So that's the number of ways of choosing that last book, but that's given that I've already picked books A and B, right? Given that, or books 1 and 2, given that A and B have already occurred. So these are dependent events. So we're just going to multiply these out here to find out the number of ways that this can occur. So how many ways can I pick the first book? Well, there's 7 books to pick from, so I've got 7 choices for that first one. Once I pick that book, there's only 6 left for the second book. So the number of ways of picking the second book, given that you've already picked one, there's only 6 books left. And likewise, the number of ways of picking that third book, given that I've already picked the first and the second one, 2 have been eliminated, so there's only 5 ways left to do that. So 7 times 6 is 42, times 5 is 210. It sounds like 210. 210 different ways that I can arrange those 3 books on the shelf from the 7 books to pick from. All right, let's talk about a couple of other terms here that we need to know about. The first one is what we call a fixed position. And a fixed position, the word fixed there is meaning that you have only one choice for that particular position in your arrangement. Again, when we have a permutation, there's an order to this. So you have to think about that order as each one of those things that goes in that particular arrangement has a particular position to it. So when you have a fixed position, we're talking about one of those elements that's in that arrangement has to be a certain item, has to be a certain object. It's got a fixed position. There's only one choice for that particular arrangement, for that particular position in the arrangement. And the other term that we need to talk about here is the restricted position. When you talk about a restricted position, that means you have more than one choice for that particular position, but not all of the choices for that position remain. All right, so you have more than one, but not all of them. It's the difference between a restricted versus a fixed position. Fixed position, there's only one choice left. Restricted means you don't have all the possibilities left, but you have more than one. So it's kind of somewhere in between all versus fixed is what we mean by restricted. All right, take a look at example 2, which illustrates this idea of a fixed versus a restricted position. On page 715, it says that you have a permutation is selected at random from the letters in the word sequoia. What is the probability that it has a letter Q in the 4th position and ends with a vowel? All right, so we've got the word sequoia is what we're working with. Write that down. Sequoia is an interesting word there because it actually uses all of the vowels exactly one time. A, E, I, O, and U show up exactly one time in that word. One of the few English words that we have like that. So, which I guess is probably why they gave us this word, because they're talking about vowels in it. But there's a couple of events that we've got to have happen here. Actually, I guess technically there's 3 events that I'm going to break this into. The first thing is it says that what's the probability that the letter Q is in the 4th position? All right, so that'll be our first event. Event A is that the Q is in the 4th spot. Put the Q in the 4th spot, or 4th position, whatever you want to say. We'll say that event B, they said the Q is in the 4th position, and it ends with a vowel. So the other event that we need to worry about is putting a vowel in the last spot. And what is that? 1, 2, 3, 4, 5, 6, 7 letters in there. So that's putting a vowel in the 7th spot. So we're rearranging all these letters, and we want to end up with a Q in the 4th spot, a vowel in the 7th spot. Well, I guess before we go any further, let's think about what we have written down here in terms of the 2 words we were just talking about, or the 2 phrases we were looking at. When you're putting a Q in the 4th spot, there's only one Q. So this right here would have a fixed position then. There's only one choice there. It's got to be the Q. The 7th position, the 7th spot has to be a vowel, which there are 5 vowels out of the 7 letters. So I have more than one option here, but not all of the options can go there. So this would be what we call a restricted position. Okay? All right. There is one last event, I guess, that we should talk about, because that only takes care of 2 of the 7 letters we're dealing with. So we're going to kind of group all these together. If you want to list 7 different events, one for each one of the letters that we're writing out here for each spot, you could do that, but I'm going to group these together. So we're going to call event C placing the other 5 letters. All right, so those are the 3 events that we've got to deal with here. All right. So we want to find out the number of ways of arranging these 7 letters, and we want to arrange them in a certain way. So the first event that I need to have happen is I got to put Q into the 4th spot, and I've got to put a vowel into this last spot, the 7th spot, and I've got to arrange the other 5 letters. So that's my event that I'm talking about, the number of ways that all 3 of these can occur. So to find out what that's equal to, we just find out the number of ways that you can arrange that first letter there, the Q in the 4th spot. So it's the number of ways that event A can occur. Since we're using the word and here, we're going to be multiplying these together. So it's times the number of ways of event B occurring there, which is the vowel in the 7th spot. Now, because the Q is not a vowel, those are not dependent events there. They're independent of each other. Doesn't matter whether what vowel I've placed there. There's still only one choice there for where the Q's got to go. And then multiply that by the number of ways of arranging the other 5 letters. Now for that is going to be dependent events that we've got to deal with. Because for arranging those other 5 letters, whatever I pick for the first letter to arrange there, there's only 4 letters left for the next choice, and so forth. All right, so let's go through this and find out the number of ways of event A occurring was putting a Q into the 4th spot. Well, there's only one choice. There's only one Q in our word, so I can only pick that one Q and put it in that one spot. Number of ways that event B can occur, that is putting a vowel in the 7th spot. Well, there are only 5 vowels out of the 7 to pick from. Out of the 7 letters to pick from. So there's 5 choices for that. Although technically there's only 6 letters left at this point because we've already taken the Q out. But 5 of those are vowels, so there's 5 choices there for that. And then we got to multiply that by the number of ways that we can arrange the last 5 letters. So for the last 5 letters, I have to start out with one letter and pick a letter to plug in there. Let's assume that this is the first spot in our word. So if I go to plug in that first letter in my word, there's 5 letters that are left to pick from. There's 4 vowels and the letter S still to pick from. But now for the next letter that I'm going to fill in, the second spot, there's only 4 choices for it. And 3 for the next, and 2 for the next, and 1 for the next. The very last letter, there's only one choice to plug in there. It's really the 6th spot in my arrangement there because the vowel is going at the end. So there's only one choice to plug in there. So there's our calculation that calculates for us the number of ways of arranging these 7 letters in this particular way. A Q in the 4th spot and a vowel in the last spot. So what do we end up with when we calculate that? We'll grab your calculator and check out what you end up with here. If you plug that in 5 times, I'll just quickly calculate that. 5 times 4 times 3 times 2 times 1. Looks like we get 600. You can try that out on your calculator and make sure that you get the same thing, but that's what I'm getting. All right. Now again, this problem here was not asking for just this number of outcomes. It was asking us for the probability. So we've also got to figure out then what's the sample space. So the number of outcomes in your sample space. In your sample space, you're just arranging 7 letters. Okay, maybe actually I should start out by saying that. S is the arrangement of 7 letters. And it's the 7 letters that are in the word sequoia. So the number of outcomes in our sample space then, N of S, is equal to, let's pick the first letter for the first spot. There's 7 letters to pick from, so I've got 7 choices there. I can pick any one of those 7. For the next letter, there's 6 choices for it, 5 for the third letter, and so forth. 4 times 3 times 2 times all the way down to the very last letter. There's only one choice for the very last spot. So you end up with 7 times 6 times 5 times 4 times 3 times 2 times 1. So if you grab your calculator again and punch that in, I'll quick punch that into my calculator. You do the same. I get 5,040, 5040. Okay, so now we can answer the question. The question was, what's the probability of this event occurring? Maybe I'll rewrite this, that our event is a Q in the fourth spot and a vowel in the last spot. So the probability of that event occurring. Well, it's the number of ways that we can get a Q in the fourth spot and a vowel in the last spot, which we found there were 600 ways to do that. Divided by the number of outcomes in our sample space, which we calculated was 5,040. And again, you can leave your answer just like that. If you want to simplify it, you can certainly do that too. Or if you can write it as a decimal, you can. But I'd prefer to see initially your calculation showing me the exact numbers that you're coming up with. And then you can simplify it from there, if you'd like. All right. Let's take a look at what a factorial is. Turns out that we have a mathematical way of representing this product that we were just dealing with when we saw 7 times 6 times 5 times 4 and so forth all the way down to 1. We call that a factorial. N factorial is defined as n times n minus 1 times n minus 2 and so forth all the way down to 1. When you are multiplying a number by a sequence like that of decreasing values, that is a factorial. By definition here, it turns out that 0 factorial is 1. 0 factorial is equal to 1. It's not 0. And the reason for that, that's what this explanation has here for us. If you took n factorial and divided it by n, it would turn out that's the same as n minus 1 factorial. So if you let n be 1 in that little equation there, you get 1 factorial divided by 1 is equal to 1 minus 1 factorial. On the left, you end up with 1. On the right, you end up with 0 factorial. So this is where the definition of 0 factorial comes from. 0 factorial is defined to be 1, based on what the definition of a factorial is. So for example, I want to find out what 5 factorial is equal to. 5 factorial is equal to 5 times 4 times 3 times 2 times 1. 5 times 4 is 20, times 3 is 60, times 2 is 120, times 1 is still 120. So 120 is 5 factorial. Now if you grab your calculator, you have a factorial button on your calculator. So go ahead and grab your calculator and let's check that out. All right, so with your calculator, if you go to your math menu, and you go over to PROB, which stands for probability, and right down there at option number 4, that's our factorial symbol. So that's where we're going to go to grab a factorial here. So if I want to calculate 5 factorial, I can type in 5, and go to math, go over to probability, option number 4, 5 factorial, and you get 120. Okay? Factorials get really big really quick. Okay, in fact, if I take something maybe as simple as, say, 40 factorial, which that maybe doesn't sound like it's that big of a calculation. 40 factorial is a really big number. In fact, that's almost half the size of the biggest number I can store on my calculator. I can only store a number up to 10 to the 99th. That's 10 to the 47th is what I'm looking at there. So that's a pretty big number. So there are some restrictions on your calculator in terms of dealing with factorials. Just keep that in mind, that as you're working with a factorial, if you're working with some big numbers, you might run out of space there on your calculators to work with those. But nonetheless, you do have a button on your calculator that allows you to do that. All right, there's a couple of permutations, special permutations that we should talk about. You'll see a couple of problems in the assignment that will deal with these. The first one is permutations with repeated elements. Again, this is defined there on page 718 in the assignment set is where you'll see this definition. But a permutation with repeated elements are sometimes called a repeated permutation. It's an arrangement of objects in which some objects are indistinguishable from others. So some of the objects are indistinguishable from the others. So think about what that means. If you can't tell objects apart, and a permutation is a rearrangement of a particular order of those objects, then if I can't distinguish the difference between a couple of objects, how do I know if they've rearranged themselves? It'd be kind of like having identical twins in my classroom, and they're sitting in the right seat when I walk in the room. I step out for a minute and I come back in, and maybe they've switched seats, but since they're identical twins, I can't tell that things have been rearranged in here. That's what we're talking about, repeated permutations. You can't tell the difference between one arrangement versus another, so how can you count them differently? That's the issue that we're going to run into here. In fact, that's the problem that we're describing here. If you rearrange those two indistinguishable objects, that would result in an identical arrangement. If they're identical, how are you distinguishing between them? And so how can you count them differently? The answer is you can't. So you do not count both of these arrangements. If I take two objects that are indistinguishable, I switch them around, and I show you that second arrangement, how are you going to tell whether I actually swapped them or I didn't swap them? It'd be kind of also like having a deck of cards. And I show you the deck of cards, it's in order, but then I take a king of hearts out of one deck and a king of hearts out of the other deck, and I swap those two. How are you going to tell that I've swapped those two cards? They look exactly the same. Repeated permutations. So here's our solution then. This is how we handle that. And the problem is we can't distinguish them, so we shouldn't be counting them separately. So here's how we handle this. We calculate the total number of permutations of all of our objects, and we divide by the permutations of those indistinguishable objects. And there could be multiple indistinguishable objects. Maybe I got a couple sets of twins in my classroom. Or maybe even some triplets. You have to divide by each of those permutations of those indistinguishable objects. All right, so let's take a look at an example to illustrate this. We're going to take letters in a word here and rearrange them, and we're going to be particular on the word that we're going to pick. We're going to pick the word Mississippi. Why do I want to pick the word Mississippi? Well, because it's got 4 S's in it. Those are indistinguishable. It's got 4 I's in it. Those are indistinguishable. It's got 2 P's in it. Those are indistinguishable. In other words, if I gave you this word right here, and then I gave you also this word where I swapped the last 2 P's in there, and I asked you which one was which, you'd go, well, those are the exact same word. I can't tell the difference. And I go, no, I swapped the 2 P's there. You can't tell the difference between the two because I've got indistinguishable objects. All right, so how do we calculate the number of permutations? How many letters are we working with? 4, 8, 11 letters here in the word Mississippi. So the first thing you have to do is find the number of permutations of the word Mississippi. Well, that would mean that you've got 11 choices for the first letter in the word Mississippi. You've got 10 choices for the next, I shouldn't say in Mississippi, in our rearrangement here, you've got 10 choices for the next letter. You've got 9 for the next, and 8, and so forth, right? 7, 6, 5, 4, 3, 2, 1. In other words, that's really just a factorial is what we just called that, right? That would have been a better way perhaps to write this. In fact, we're going to rewrite it that way, but I just wanted to write it out first this way to think about it in terms of an arrangement of objects here that are dependent events here, picking one letter and then picking out of the remaining letters the next one and so forth. And I have to divide this by now the permutations of the indistinguishable objects. So let's deal with the I's first. So I'll do these in different colors. Let's take the I's here. There's a total of 4 I's. So the permutations of those 4 I's, I could pick any one of the 4 I's first for the first arrangement. And then there are 3 left for the next one, 2 left for the next one, and 1 for the last one. The permutations of those 4 I's is 4 times 3 times 2 times 1. There's 4 choices for the first I that I could pick, 3 for the next one, 2 for the third one, and finally 1 for the last one. Let's deal with the S's next. Again, notice you got to deal with all of the indistinguishable objects. So I've got 4 S's. Same story here then. I have to multiply that by, I could rearrange those 4 S's. I got 4 choices for the first S that I pick, 3 for the next one, 2 for the next, and 1 for the last. And then finally, there are 2 P's. So I got to also multiply by or divide by the permutations of those 2 P's. There's 2 P's to pick from, so I can pick any one for the first one, which means it leaves me only 1 left for this last one. So in other words, this is equal to, this is really 11 factorial divided by 4 factorial times 4 factorial times 2 factorial. I'll let you punch that in your calculator and see what you end up with there. But that's the number of permutations of the word Mississippi. Again, if you just take the 11 factorial, the problem you're going to have there is that if I take one of those permutations, it's going to be this word Mississippi. And then if I take and swap the 2 P's, that's another one of the permutations you actually have counted. And you're going to go, wait a minute, those are indistinguishable. They're exactly the same. And I agree with you, and that would be why we have to eliminate those. We're dividing those out of there. 11 factorial divided by the 4 factorial times 4 factorial times 2 factorial. All right, let's talk about the last of the 2 special cases here that we need to talk about, which is a circular permutation. And again, you'll see this in the assignment there in the problem set. On page 718, they'll describe this for you, but I want to make sure I mention it to you as well before you see those problems. A circular permutation is an arrangement of objects in which the objects are arranged in a circle. You could be sitting around it could be people sitting around a table, and that's a permutation of those people around that table. Could be a variety of things that you're arranging in a circular manner. So here's the problem that arises with this. Let's suppose you got 4 people sitting around a table. And we say, okay, that's one arrangement. And if I say, okay, everybody stand up and take move 1 seat to the right and sit back down, when I look at that arrangement, I go, wait a minute, everybody's in the same order. Everybody's sitting with the same person on the right of them as they had before, and everybody's sitting with the same person on the left of them as they had before. Moving everybody, or moving every object, I should say, in general, 1 position to either the right or the left would result in an identical arrangement. So in other words, we've counted some permutations that I can't distinguish between them. So we do not want to count these identical arrangements. That's the problem. So what's the solution? Well, we just fix one of the positions here. Oops. So we'll fix 1 position around the circle. We'll just take that first object and say it's a fixed position. So there's only 1 choice for what to put in that spot. And then we'll calculate the permutations for the remaining objects. That will take care of this idea of rotating things around and ending up with the exact same permutation. All right, so let's take a look at an example to illustrate this. So find the number of circular permutations of the letters A, B, C, and D. Well, let me start off with just a picture of what we're describing, at least a couple of examples here of illustrating what the problem is. Let's say I've got this little circle here, and I'm going to arrange my letters A, B, C, and D. So clockwise from A, I'd hit B, and counterclockwise from A, I'd hit D. All right, notice that's how that would be set up, and you can go through and talk about each one of these objects and what's to the in the counterclockwise and clockwise direction from it. If I take each one of those objects and say, okay, I'm going to move every one of those 1 spot to the right, I'd have A here, B here, C, and D. And now, if I look at what's on the left and right, or the clockwise and counterclockwise direction from each one of these objects, they're exactly the same as the first one. These are indistinguishable permutations. So our problem is that I've got to eliminate those indistinguishable ones. So this is why we're going to fix the first position. I'll take the A, for example, and say that's my fixed position. I'm going to say there's only 1 option for where that A is going to go. I don't need to include the A going at the top versus the right versus the bottom and so forth. I'm fixing its position. and then permute all the other objects there, arrange all the other objects. So there's 3 objects to pick from, so there's 3 factorial ways to arrange those other objects. So we fix the first one, and we arrange the rest. All right, and that's what you'll see there when you get to those problems. And at the end of the assignment, they'll give you some circular permutations here as well as some repeated permutations. All right, that right there is the end of section 14.4.